So the informal title of this talk would be OpenMP does not scale. And I started to be more vocal about it because I see and hear too many people saying, oh, OpenMP doesn't scale. And actually, in all the cases, that turns out not to be true. There's something else going on. So that's what I want to talk about. That's a really common and very annoying misconception. So think about it. A programming model cannot not scale. That's just a set of recipes how to get to your goal. Things that cannot scale are like the implementation. If I would take 3 days to create my threads, it wouldn't scale. So the implementation can have flaws, inefficiencies. Another thing is that I would never say people buy the wrong hardware. They buy the hardware that doesn't match the needs of the application, like a lot of bandwidth or whatever. You can imagine. Those are reasons. But actually, it could also be you. You wrote OpenMP, and one of the beauties of OpenMP is easy to use, but that doesn't automatically mean you're off the hook with performance. And I'll talk a little bit about that. So I'm going to give a top 10 of dumb things to do, and of course nobody here is doing that, but I just want to show common things that I see that cause scalability issues. First of all, the big mistake is you should always use OpenMP. So a dumb thing to do is don't use OpenMP. Well, one more serious thing is that you start with a code that doesn't run well on a single core. What do you think will happen on 10 or 100 or 1,000? Do you think magically it will go better? My claim is it will go worse. And the simple reason for that is very often badly performing code means you go to the memory system too often. You have a lot of cache misses, you go to the memory system. Now you do that with 10 threads, 100 threads, 1,000 threads. Your interconnect will die. So that's rule number 1. Find some ways to improve the performance, play with compiler options, maybe restructuring your code, it's really up to you. But make sure that your single thread performance is reasonably okay. Rule number 1. Then, a dumb thing to do is don't use a profiling tool. I make this challenging. I mean, you got to have a lot of coffee to get it. A dumb thing to do is don't use a tool. People come to me and they say, oh, I know where the time is spent. Well, that may be important for your physics or chemistry, but actually for the computer, it could be something totally different. You wouldn't be the first one where you said, oh, gee, I never thought that was so important because it didn't play a role in your modeling. So always use a tool. Pick the one you like. The tool will tell you where you're spending most of your time, and that's the part to focus on. Another dumb thing to do is use an excessive number of parallel regions. Each parallel region carries overhead. So once you start having them all over your code, it adds up. And again, I'm talking about scalable performance. I'm talking about what are you going to go to 100 threads, 1,000 threads. That's what I'm talking about. So a better way, I should be kind of constructive, a better way is to have large parallel regions and put the work in there. And if there's no parallel work, you can, for example, put it in a single region, if only one thread has to do it. So another common mistake is excessive use of shared data. Shared data is very convenient, but when you modify shared data, cache coherence will pitch in, and that can lead to all sorts of performance side effects that I won't go into right here, but be careful to share data. Only share data when you have to. Try to do computations, for example, on local data as long as you can, and then when you're finished, you may write it back into some shared data structure, and that's fine. And then other threads can pick it up. Think about it from a locality point of view. That was 5 reasons, but I promised you 10. Another dumb thing to do is to forget about the no wait clause. Just a quick show of hands. Who's familiar with the no wait clause in OpenMP? Okay. Not enough hands, go up. Here's the thing. When threads synchronize, they typically do that in a construct called the barrier. All threads wait in a barrier until the last one has arrived and you continue. Now, sometimes that's overkill because the part below it is independent of what you just did. You may initialize some of the things and something else is independent. Then OpenMP on certain constructs has a very convenient clause called no wait. And it does exactly what it promises. The threads won't wait. They'll immediately continue with next piece of work. You'll save a barrier, and barriers are inhibitor for scalable performance. Small thing. You wouldn't put that in your first OpenMP code. But once you start doing the fine-tuning, and for example, the tool may tell you, you're spending a lot of time in the barrier. Well, maybe I can use the no wait. Okay. I see a lot of locking where you really think, is that really worth locking? I mean, locks are useful, but again, I'm currently looking at a code where the locked code block is like that, and it's totally killed in the lock performance. So when you start doing locking, be careful. Another common one is, by default, OpenMP will schedule the threads in a static way, so you all get the same amount of iterations, for example. Well, what if there's a load imbalance? What if not every iteration takes the same time? Think about the dynamic, guided scheduling things. Often overlooked, again, a profiling tool should tell you that that's a problem. All right? Another thing which sadly you cannot ignore these days is CC-NUMA. I like to say we didn't ask for CC-NUMA, we got it. And there's a good reason, because with the CC-NUMA system, as you add a socket, you add memory bandwidth. Because each socket has a portion of the memory, so you get more scalable bandwidth, but it's on you to take advantage of it. If you ignore it, and even simple algorithms we can show won't scale. Again, it's not pretty, but it's the way it is. So don't ignore it. And OpenMP has nice support to handle CC-NUMA. And the worst thing to do is forget all of the above that I just explained to you. So go through the checklist, make sure that, again, don't forget, start with a profiling tool. I now want to show you a case study. And the case study is from graph analysis. And I'll have to skip all the details. I'll be more than happy to talk offline about it, longer than you probably like. But I'll show you the results, like what happens along the way. So what's a graph? Very simple set. A graph is a mathematical abstraction. You have the nodes, or vertices, and the links between those called edges. An edge is defined through the relationship. And the easiest one is people. You got people in your network, and do you know each other? Does C know D? If so, I draw a line, an imaginary line in my data structure, and that builds a graph. And one of the common things that people like to do is search. You want to search through that graph. You want to find somebody. And you know the social websites, they tell you like who's connected to you and who you may be interested in. That's all done by searching through the graph. So searching is a very common operation on graphs. There are other things you do on graphs, but a search is one of the things you pretty much always do. And from a benchmarking point of view, the score is not megaflops because you don't do any floating point operations. It's how many edges can you traverse per second. How quickly can you go through your data? Okay, that's the number I'll be using and the vertical axis on my chart. It's called TAPS, traversed edges per second. So I'm looking at this benchmark. It's written in C. It's been parallelized with OpenMP, or obvious. You can play with the size of the graph. The graph is generated for you. It's a synthetic benchmark. And that's controlled through a value called scale, and that's what you'll see on my charts. The number of vertices, the number of nodes, is 2 to the power of scale. So a scale factor of 10 will give you 1,024 nodes. And each node, on average, has 16 connections to others. Okay. And you crank up the size of the graph that way. So I took that benchmark, I pulled it from the web. Anybody can do that. I ran it, and I didn't try on other hardware, but I think this is fairly generic based on what I found later. I ran it on a 2-socket system, and the performance is terrible. It's game over after 16 threads. And this was a fairly small graph, 35 gigabyte, scale 26. All right. So many, and I have that experience very fresh from last week, said, oh, let's use a bigger machine. This machine is not big enough for what we're doing. So you take a bigger machine, and it's actually a little bit worse. Wow, that's a bummer. Okay, the next thing that people do, and of course I'll explain why that is, but the next, oh, that graph is too small. Let's take a bigger graph. See if we can have an easy way out. Well, the curves are nearly identical. It doesn't help. There's no easy way out. Going to a bigger machine doesn't help. Increasing the problem size, none of it that helps. So what are we going to do? We got to go under the hood. We got to find out what's going on. And again, we got to start using a profiling tool. So I used our profiling tool, and what I did, I picked the value, the small 35 gigabyte, because that was the one that didn't scale. So that's convenient to focus on a small case. So I picked the smallest case that doesn't perform well. And what I do, I look at the overhead as a function of the number of threads. And all these bright colors, like orange and red and pink, they're all bad news. They're all some sort of OpenMP overhead, like atomic operations, atomic weight, waiting in a critical section. All these things are the cost of parallelization. And to me, the telltale sign is this one. It's an achievement in itself to take a sequential program and manage to get 7% overhead while you're not going parallel. What does that say? That says that this code has been poorly parallelized, and in this case with OpenMP. There's too much overhead you go through, even on a single thread. So even without looking at the code, you know that's bad news, and as you see, very quickly game over. This is why this code doesn't scale. Another thing I looked at was the bandwidth. Maybe there was a bandwidth issue, and indeed, on this system, two-socket system, the theoretical peak performance on the memory bandwidth is about 130 gigabytes a second. I only get 50. And when you look at this in more detail, you can see it's pretty much all read bandwidth, 90% reads. And what you can see here, I distinguish between two sockets. Blue is socket 0, orange is socket 1. Well, orange is hardly visible. It all comes from one socket. What does that say? This is not CC NUMA friendly. I'm not using the bandwidth in my system. So to summarize what I saw, excessive communication, it explodes as you increase threads. As a result, I can't use all the threads, and I can't use all the resources in my system. So I really get bitten. Bandwidth is not balanced. So what do? Go into the source code, use your profiling tool, and fixing it one by one. And that's what I did. One by one, I found some room for using a lower level atomic functions. That's questionable whether you want to do that, but I want to grab everything I could. So that's what I did. So that's what I call the secret sauce, and BO here stands for bad OpenMP, and this means better OpenMP. I don't pretend that I fixed everything or found everything, but as the results are, it'll definitely look better. I want to show you, again, profiling tools. I used our own profiling tool. And what this shows is a timeline. As the program is running, I color code the bad things happening in my program. And there's a lot of detail here, but all these colors are kind of bad news. And this is before, and this is after. And one thing you may notice is this part shrunk to this one, and the blue is idle time. This code managed to get slower as you add threads, that part. That's not kind of the goal of parallel computing. I think we have a different goal here. So one thing I quickly did, jam it in a single region as a hack, and actually I got better throughput. Okay. Of course, you have to look at a more fundamental fix when you have more time, but that was an easy kind of thing to do. And then you see these pink colors and red. They're much less here. They're still there. I still need to do my barriers and whatever, but it's much, much less. And it translates to much improved performance. This little worm was my original performance. And I got way, way better performance. All right. I wasn't done though. This code also had this. So what I did, I fixed the OpenMP. Now I start looking at the memory side of things. So that's the better OpenMP to memory optimizations. That's what it stands for. So, first of all, this code did not know about first touch placement. What that means is, on a system, by default, the thread that initializes the data owns it. So if only one thread initializes your data, all the data will end up in one socket. So a simple thing to do is parallelize the data initialization and spread out the data. It's a very simple thing to do in most cases, and it gets you going. It may not be optimal, but it certainly helps. So I looked at that. Another thing is, which is not visible in these charts, this code is, the data access is random. It's jumping all over the memory. When you see that, use large pages. And I hope you're familiar with that. You can increase the size of a virtual memory page on a system. You do that in software. You don't have to reboot or something. There's ways to increase the size of your page. And again, if you want to know the details, talk with me offline. So that's about the random memory access. And it definitely needs large pages. I also looked at the way memory was allocated, and it was really doing some dumb things like reallocating the same thing for every search. And it doesn't change. That's not smart. I mean, that's a simple logic that will help. So I did a lot of those things as well. And now look at the bandwidth. I got near peak performance. It's actually peak performance. That's the kind of chart you like to see. And when you look at the accumulated benefit of it, I looked at scale 29. That's about 280 gigabyte of memory needed. Scale 30, half a terabyte. Scale 31 is a little over 1 terabyte of memory needed. And this red here is the original performance in terms of traversed edges per second. My OpenMP magic helped me to get substantially better performance, and then I add memory to it, and I get way, way better performance. I like to translate things like speed up to what I call real money. What does that mean in terms of search time? What it means in this case, a search time of 12 hours reduces to 10 minutes. That changes your way you can do your science, your work. You no longer have to wait a day. You go and get a coffee and you got your results. That's what these speed ups mean, and that's, I think we often forget that speed up is a number, but that's what it translates to. All right. And I couldn't resist. I took a larger graph, more than 2 terabytes, and indeed, I keep on getting the benefits. I keep on getting, this is, the reason I included this slide is when people come to me and say, shared memory, it doesn't scale. Look at the number. Close to 900 threads in one single system. Don't tell me shared memory doesn't scale. Compare that with that little red worm I had in the beginning. Yeah. All right. I wanted to see the benefit of both optimizations. So what I'm showing you here, the red line is what happened when I fixed the OpenMP as a function of the graph size. And you see for the small graph, I got about 25. It reduces to about 20. But 20x is a huge improvement. I mean, that. And then adding the memory helped, not as spectacular, not a 25x, about 3x. But look here. Now, large graphs actually do better. That's exactly what you want. Okay. Then I got another idea. There's a year in between. I mean, it's not that I sit at my desk and I crank out all these things one after the other. I mean, there's some time in between. I dropped it for a while. I revisited this code. No, wait a minute. I can do some better OpenMP. And that's the blue line. And by the way, this is on this 8-way box that did so poorly in the beginning. Remember, it wouldn't be better than the 2-socket box. I didn't include the 2-socket numbers here, but it definitely scales now. And you can see by playing a little more with the OpenMP, I get another significant boost. So overall, compared to the starting point, I get about 50 to 70x performance improvement. Okay. So what's kind of the takeaway, the methodology? If a code doesn't scale well, use a profiling tool. Whenever people come to me and says, could you help with the tuning? I'll only kick in when you show me the profile. Where's the time being spent? All right? Use that checklist to go through bottlenecks. Just go through them. How about my barriers? How costly are they actually? And one by one. It's not like you do that in one big blast. You reduce the barriers, you run again, check with your profiling tool, and you see an improvement. Wait a minute, that's going the right way. Now, sometimes it goes the wrong way. Don't get me wrong. You have this brilliant idea, and the code is slower. That's part of it. And later you realize the mistake you may have made. All right. So it's an incremental approach, absolutely. but very rewarding. To summarize, again, OpenMP cannot not scale. There are other things that cause it not to scale. So please don't blame OpenMP anymore in the future. Blame something else. And in most cases that I see, it is the application. Somewhere there's a, and it could be hidden. I mean, it could be hidden, and again, that could be nasty, but it's not OpenMP itself. All right? But in most cases, you find a way to reduce it or even fix it, eliminate it. That's the goal. But certainly minimize the pain. One other thing, when you want to go for ultimate scalability, tackle everything. Even what doesn't seem to be important on 8 threads or 16 threads will get to you when you go to a higher number of threads. All right? And of course, the reward is enjoy a very scalable application. And that was my talk. Remember, it's not that OpenMP doesn't scale, bad OpenMP doesn't scale. So that's my new logo in the future. Thank you very much for your time. And yeah, thank you.